Hello everyone, I am Prajakta Belsare, a graduate student at the University of Alabama. Today I am going to present a paper, Computation of Cigarette Smoke Exposure using Bioimpedance Sensor on behalf of my team, Dr. Seyurek, Dr. Imtiaz, and Dr. Sazonov. Before going ahead, I would like to thank all of you for being here today. Today's agenda is to discuss the motivation behind choosing this topic, an overview of available methods, proposed method, results, and conclusion. According to Center for Disease Control and Prevention reports, cigarette smoking is the major preventable cause of deaths in the United States. It harms nearly every organ of the human body, as it can be seen in Figure 1. Even though efforts have been made to create awareness through anti-tobacco campaigns and smoking cessation programs, there is not a significant reduction in rate of smoking. Researchers think it is important to understand smoking behavior and to provide the information about smoke exposure in order to increase the awareness among people. Similar to health trackers like Fitbit, a cigarette smoking tracker can be a helpful intervention. The smoking behavior assessment can be done by using self-report, mouthpiece-based topography devices, biomarkers of smoke exposure, and wearable sensors. Self-report measures number of cigarettes, number of puffs, duration of cigarette. However, it won't be able to provide any information regarding the volume of puff or duration of puff, etc. On the other hand, the puff topography can provide little bit more information, such as duration and volume of puff, also duration between consecutive puffs. However, it fails to report information regarding post-puffing behavior. Biomarkers of smoke exposure provides information regarding carbon monoxide and cotinine level, etc. In a nutshell, the existing methods can provide some information regarding puffing, but there is no reliable or objective method for measurement of post-puff information. As post-puff information such as inhale exhale duration and volume, smoke holding duration can provide greater insights about the amount of smoke exposure. This leads us to find an alternative method that can provide us with the information about the post-puff behavior. In our lab, we have developed a personal automatic cigarette tracker, PACT 2.0. This is a wearable sensor system that consists of an instrumented lighter, a hand device, and a chest device. For the proposed study, we are using the data collected from bioimpedance sensor of chest device only. Figure 2a shows the chest device worn by the participant during the study. Figure 2b shows the chest module of PACT 2.0. This device is placed at the thoracic level of the participant. Figure 2c shows the electrode placement for the chest device. Using PACT 2.0, we have conducted a human study. Table 1 and 2 gives a brief overview about the human study we conducted at the University of Alabama. We had recruited 40 medium to high smokers, that is, those who smoke more than 5 cigarettes per day and have carbon monoxide level greater than 5 ppm. This study was conducted using a predefined protocol as shown in table 3. The participants were asked to wear the PACT 2.0 devices for approximately 24 hours. The participants spent 2 to 3 hours in the lab and approximately 21 hours in the free living environment. In the lab session, the participants were asked to perform various activities, including 4 different smoking activities. The participants were video recorded during the lab session. These videos were annotated to extract the puff duration, inhale exhale duration. These annotations were considered as the ground truth for evaluating performance of proposed method. As shown in figure 3a, the breathing exhibits a distinct pattern during cigarette smoking. This pattern consists of an apnea or puff followed by an inhale, optional smoke holding, and an exhale. If we can successfully identify the start of the puff, end of puff, inhale point, and exhale point, as shown in figure 3b, we can get post-puff information from this breathing signal, such as inhale-exhale duration and inhale-exhale volume, smoke holding duration, etc. Thus, we propose the use of breathing signal captured by bioimpedance sensor for computing smoke exposure metrics. For obtaining the smoke exposure metrics, the raw signal captured by bioimpedance sensor was first pre-processed to remove noise, baseline wander, and motion artifacts. Next step is signal calibration, to calibrate the signal in terms of liters for extracting volume information. After signal calibration, we will apply the RSEM, Respiratory Smoke Exposure Metrics algorithm, to compute the smoke exposure metrics. Figure 4 shows the raw breathing signal. As you can see here, there is a baseline wander, noise, and motion artifacts in this signal. This raw signal is pre-processed using a low-pass filter followed by a high-pass filter and Shevetsky-Golay filter. Figure 6 shows the filtered signal, which looks pretty clean. This pre-processed signal is then calibrated in terms of volume according to the lung capacity of each individual to obtain the volume information corresponding to each smoke inhalation. Now let's discuss what is respiratory smoke exposure metrics, RSEM is. RSEM is defined by us to compute the puffing as well as post-puff information from breathing signal. In RSEM, we have defined the smoke exposure parameters, namely puff duration, inhale-exhale duration, inhalation duration, smoke hold duration, inter-puff interval, as shown in the figure 7. Puff duration is the duration for which a smoker drew smoke from the cigarette into the mouth. Inhale-exhale duration is the duration for which smoker inhaled the smoke drawn from the cigarette into the lungs and then exhaled the smoke partially or fully through mouth or nose. Smoke hold duration is the intermediate step between the inhalation duration. This is the duration for which smoke is held inside the lungs after inhalation. Inhalation duration is the duration from the start of the puff till the end of smoke exhale. Interpuff interval is the duration between two consecutive puffs. Our aim here is to detect PS, that is start of puff, PE, that is end of puff, IP, that is inhale point, EP, that is exhale point, and EXS, that is start of exhale. In RSEM, we also define the volume parameters such as inhale-exhale volume and volume over time as shown in figure 8. Inhale-exhale volume is the volume of smoke displaced between inhalation and exhalation. The volume over time is the volume of smoke passing through the lungs of a smoker per unit time. Figure 9 shows the detection of start of puff, end of puff, inhale point, and end of exhale corresponding to each smoke inhalation during cigarette smoking. The solid black line denotes the start of puff, dotted line denotes the end of puff, the black markers at the peak and valley denotes inhale point and end of exhale respectively. For evaluating the performance of proposed method, we developed two hypotheses as shown in table 4, where we compared puff duration and inhale-exhale duration obtained from breathing signal captured using bioimpedance sensor with ground truth information. In hypothesis 1, H0A, the puff duration obtained from bioimpedance signal and video is statistically the same. That is our null hypothesis. And our alternate hypothesis is that they are statistically different. Similarly, in hypothesis 2, the inhale exhale duration was compared. Table 5 shows the results of t-test at alpha equals 0.05 for comparing results of proposed method and ground truth. The p-value for puff duration comparison and inhale exhale duration came out to be greater than the alpha value, which denotes that the puff duration and inhale exhale duration obtained from the proposed method and ground truth are statistically the same. This indicates that the breathing signal captured using bioimpedance sensor can be used to compute the cigarette smoke exposure metrics. The results show that we can successfully compute the puffing information as well as post-puff information from the breathing signal captured by bioimpedance sensor. Currently, RSEM is a semi-automatic algorithm. However, it can be improved to work automatically to study free-living smoking behavior and corresponding smoke exposure metrics. Thank you for your patience. Any questions or comments?